So today will be about the cybersecurity challenges of energy systems, and I will try to connect a little bit with the previous talk of Paul about imprecise measurements and how they affect also in terms of cybersecurity. Before doing so, being at KAUST, being in Saudi Arabia, is a little bit of a lot of questions are being raised sometimes. So I will spend the first 3 minutes of the presentation to say where I come from. Not originally, but where I work. So I am based at KAUST. KAUST is a postgraduate university only. We don't have undergraduate programs. Located around 60, 70 kilometers north of Jeddah, which is the second largest city in Saudi Arabia, on the west coast of Saudi Arabia, on the shores of the Red Sea. So essentially, see where we're located. And this is just a picture of KAUST, in which the interesting fact is that whoever works at KAUST lives also at KAUST. So it's a community of having from anything from schools, university, of course, hospitals, markets, restaurants, etc., etc. Saudi Arabia is changing a lot in the last couple of years. So nowadays you can visit as a tourist, where in the past were not possible. So there are many things one can do in Saudi Arabia, and believe me, the Red Sea, it's an amazing place to be. And if you like diving or sea sports related activity, that's a perfect place to be. Just a few facts about KAUST. As I mentioned, it is a postgraduate-only university. It is a new university. It was established 2009. We have around 1,200 students, all of them either master or PhD students, most of them international. We have around 100 nationalities in the campus. And we have around 7,000 to 10,000 community members. A lot of postdocs, around 500 postdocs, considering the number of faculty that is around 200. And as the name mentions, we're a science and technology university, so we're focusing only on science and technology related research. We have a lot of collaborations, mostly with Europe, but also North America and Asia. So despite being in the Middle East, we have a lot of collaborations worldwide. Now, as Peter mentioned in the introduction, I work on secure and resilient systems with a primary focus on power grids and power, but we have also work that is can be classified the world of embedded systems, embedded controllers on their hardware and software kind of areas of security. Just to conclude this introductory part of the talk, this is different configurations that we have done in the past in different studies to kind of investigate cybersecurity and resiliency challenges in power systems, and to connect with the previous talk. This configuration here was a setup we did in 2018 in order to study GPS spoofing in PMUs, right? So what you see here is RTDS, a real-time simulator in which the PMU outside the loop. We created a Faraday cage in the lab here to spoof the signal of the GPS signal coming from the GPS antenna. Faraday cage because it's illegal to try the spoof GPS. So we made a small Faraday cage in the lab in order to spoof this GPS signal coming from the antenna from a spoof signal generated from USRP, software-defined radios, and then transmitted this signal back to the RTDS, where we implemented control and protection mechanisms to see how this less than 1% error that is allowed in PMU measurements can have an effect in the phase angle of the measured phase angle in PMUs. And by doing that, we're able to shift these measurements multiple times in order to cause 7 degrees phase deviation, and then initiate control and protection and doing some actions with. On the upper right figure, I'm going to talk also a little bit about later. This is a setup where we did firmware modification attacks on solar microinverters. So we have the whole HIL type of connections from getting the proper DC supply or solar emulated input to the inverter, and then having the configuration set up right here that kind of over behavior of the inverter as it behaves on the grid. And then on this kind of figure here, we show that besides this physical layer or power system layer types of simulations, we do also co-simulation in terms of network layer, right? So we try to simulate not only components of power systems, but also co-simulate the same clock speed with the communication layer in order to see different effects. Okay, going a little bit to the technical content of the talk. As you know, the conventional operation of power system is hierarchical, centralized in terms of nature, but things are kind of changing, right? So one thing that is changing is the fact that we have seen that conventional power plants are kind of going away. Germany shutting down most of the oldest reactors in 2022. China, US, India are canceling all coal-fired power plants. At least that was the case a few months ago. In 2018, UK announced to shut down all coal power plants by 2025, right? So, in contrast, DG, distributed generation, is on the rise. By 2025, we're gonna have around $200 billion estimated kind of distributed generation installed around the globe. As you can see, instead of those fossil fuel-based generation, we have a lot of PV and other renewable distributed non-rotational generation being increased every year. In 2020, we had 256 gigawatts added worldwide. And the most important thing is the fact that the newly installed renewable power generation increasingly cost less than the cheapest option based on fossil fuels, right? So PV and energy storage have seen the sharpest cost decline in the last decade, with 82 and 85% respectively, followed by offshore wind, which is 49%. The second thing that is changing is also that the load is no longer the same, right? We have installations and preparation into power systems, a lot of electric vehicles that are changing the load landscape. Battery electric vehicles are keep increasing around 6% every year. And the other thing is the fact that we have started seeing that ISOs, independent system operators, in the past being able to match variable demand, but now they need to also match the variable supply that is kind of being increased due to the increased distributed generation and renewable energy generation. So this essentially puts us extra strain on the system in the evenings when we don't have this renewable energy generation being generated. So we have this controllable or the controllable fossil fuels type of generation need to also ramp up during this time in order to meet this not variable demand, but also variable supply. So load also is changing in addition to generation. Besides this, there are many other paradigm shifts. Besides having no synchronous players, all those electric machines are kind of replaced by power electronics based machines. We have the regulated energy markets. We have sensors and actuators being re-instrumented instead of the electromechanical relays and devices that we have in the past. So we can say in a nutshell that future power systems are coming closer to the people, right? They come power electronic space instead of electric machine based, and all these distributed compatible players, they're closer to the people. And there are many, many benefits, right? Besides having sustainable local and green energy, we have less pollution, reduced greenhouse gas emissions. live off the grid nowadays, and there are many other benefits one can enumerate because of this transition. At the same time, right, one can say that these non-synchronous players, they are not always coordinated. Instead of being controllable and reliable, we have less system inertia, so that could be a problem, right? Sometimes monopolistic markets, they have the oversight of state or public commissions, and the regulated energy markets, some may say that they don't necessarily increase competition, right? And they do not necessarily reduce the price of electricity, as one may say that was the goal. And then in terms of electromechanical components, we had relays in the past, like they could live 50, 60 years. Now, instrumented sensors and actuators need to be updated due to security vulnerabilities. So they introduce these cyber vulnerabilities. So besides all the benefits, we can also see the other kind of side of the story here, that there are also some downsides from these transitions. As a result, what we have seen in 2016 and 2019, two huge blackouts, one in Australia, one in UK, that essentially, although initiated from a lightning strike and severe weather conditions, they were result due to improper control configurations, fault right-through configurations of those wind farms. So in both cases, wind farms and renewable energy generation played a role in those blackouts. Also, we have seen operational disruptions due to the renewable energy generation orbits. 2009, in March 2009, Utah in US, what we have seen that firmware vulnerabilities were being exploited by adversaries that caused operators not having a picture of the grid for more than 10 hours, right? That was not a targeted attack. It was a vulnerability that was exploited by an actor in a large scale. Those Cisco essentially routers were also installed in power grid related installations, and essentially the vulnerability caused those routers to be rebooted every few seconds, essentially making the operator to have blind spots of the system for about 10 hours, right? No blackout, but essentially blind spots for the operator for about 10 hours. So these kind of vulnerabilities introduced from the instrumentation of the sensors and the actuators. So the question that we all try to answer is how to keep our lights on, right? Before answering this, right, let's put this into something that cannot change, right? Renewable energy, power grid, this is a thing, an equation that will not change, right? This is something that we take for granted. So the question is how to solve this equation, reducing uncertainty and the cost, right? That cost, it's all about economic factors, also uncertainty, right? So this is more of a systems problem and less than a power system problem, right? Power system engineers, we know exactly what to do in order to solve a lot of problems, but essentially we want to solve this problem, reducing uncertainty, reducing cost, and also having in mind that we can no longer rely on communication networks securely, right? And embedded controllers. Okay, so if we go back to the initial kind of goal, we need not only sustainable local and green energy, but we want also resilient and secure energy. Okay, so in the next part of the talk, I will focus essentially on two types of attacks that we have done in the past in order to essentially show, right, that the grid, from the introduction of renewable sources, it kind of also brings different types of attacks that need to be addressed. Okay, so the first attack from the red team side, right, that I would like to talk. So in security kind of language, we always talk on red team and blue team, right? It is a common kind of language in security evaluations. We want to play the role of attackers, right? And then the role of defenders, the blue team, and then we do that in a loop in order to test our system all the time in a loop, right? So in this type of study, we essentially wanted to analyze what will be the firmware modification attacks on solar microinverter embedded controllers employed in power systems, in this case, microgrids, right? So essentially our goal here is to somehow modify the firmware of inverter controllers. At the end of the day, we're talking about microprocessor-based devices, right? They are typically non-OS, not having an operating system. So they have a firmware that is operating in a single-threaded super execution. So we want to modify this firmware in a way that somehow will have a malicious effect on the system. In our goal in this particular study, what we modified the control behavior and the MPPT set points, maximum power point tracker set points. This is a circuit employed in solar inverters, typically a DC-to-DC converter that tries to maximize the available energy that the inverter gets from the connected solar modules and transmit it into the grid, right? So the goal here, the adversarial objective, is to modify those set points in the firmware of the inverter. So in this particular study, threat model, what are the assumptions of the attacker? We assume an oblivious adversary. You don't have to have a full observability of the system, of the cyber physical energy system, right? You only need either physical or network access to those inverters in order to modify their firmware, right? It depends from the model of operation, if you can modify the firmware online or through the network, or you need physical access to the inverter, right? So in terms of the resources, the attacker can be a script kiddie, right? It can be something minimum, or it can be a state-funded kind of criminal organization. So what we did in this study, right? We did not only theoretically did the attack. We had a solar microinverter in the lab connected in the loop with the simulator, right? Which we essentially simulated for what they actually inverted in order to test the firmware modifications effect back to the simulator, right? So we essentially had a hardware in the loop connection, having the inverter in the lab, doing different types of firmware modification attacks, mostly targeting the inverter conversion process by tampering those MPP. And what we did, different types of simulations, right? Electromagnetic transient stability simulations to evaluate these small signal inverter performance, but also to investigate frequency and voltage stability within that simulated microgrid, and then different types of case studies in order to analyze the impact. The important, right, is essentially to keep in mind, right, different kind of characteristics of the behavior of the microgrid in terms of load profiling and microgrid generation profiling, because as an attacker, I want to find the best timing in order to implement this attack where solar irradiance is during peak time. So the inverter kind of contribution is at the highest peak during operation. So also different load profiles will have a different effect where it is being modified during those ramp-ups of load profiles. The second study I want to briefly talk about is what we call load altering attacks, right? So we talk about firmware attacks on inverter controllers, right, at the kind of edge. We go one step beyond, right? We go further to the edge. We go into loads now. Where the goal here is to essentially, in a large scale, try to control the load, right, of a system in order to have high spikes, right? So the goal, the adversarial objective, as you can see on the last bullet point of this slide, is to trigger sudden demand increase or decrease of high wattage appliances or DRs. The keyword here is IoT, right? So the goal is to have IoT connected devices in a way controllable in a large scale, right? Think about smart laundry machines, right? Or smart refrigerators or smart ACs, right? Con Edison in New York, they have a program in which they give you an embedded controller, you install it on your AC, and essentially you are able to control it remotely. You send all these data also to them, and they kind of optimize the AC operation for better system operation, right? Imagine this device, right, had a particular vulnerability. An attacker can exploit that vulnerability in a large scale, right? So this is what we're talking here, exploitation of a specific vulnerability in a large scale of IoT connected high voltage appliances, AC, laundry machines, refrigerators, etc., etc. So it's a botnet type of attack, right? So in terms of threat model, we assume an adversary with limited knowledge. As an adversary, I don't need to know the topology of the network. All I need to know is essentially the vulnerability to this device that can exploit in a mass scale, right? And I need remote access and non-possession of the target devices, right? Essentially, we did a study recently and we showed that in a city with 500,000 population, if you are able to control HVAC systems of 5 buildings, you can cause these load balancing attacks to be realistic, right? In terms of resources, right, you need to determine adversaries with significant resources to material such sophisticated attacks, because you may need access not just to exploit one single vulnerability of a single device, but different types of vulnerabilities of different models of devices. So in terms, apparently you cannot go and test that in a real system, right? You can simulate, right? So in order to simulate this type of attack, right, in simulators, you need to kind of assign different load profiles of loads and also DRS assets in order to kind of investigate different load increase and profiles, the effect that will have in the frequency, right? That's one thing. The second thing that we need to take into consideration is the attack duration, right? Whether this load or DR kind of increase or decrease change, right? It takes for 1 second and 30 seconds of pixel, right? And then you need coordinated attacks and synchronous and different kind of hotspots. So besides duration and different load profiles, you need to know where essentially different hotspots will cause different problems, right? So here you see that if you have load increase and frequency have a kind of a decrease, and then be able to relate that with your studies, right? But right, we know that the system is kind of robust, right? We have different frequency kind of controls to protect against those sudden decrease or decrease, right? For example, if you have more than 61.7 hertz in the North American system, you have over frequency generation tripping to protect your generator, or if you have below 59.2, essentially you have load shedding in order to protect against the system, right? So one may go and take real-time simulators like Typhoon or Opal or RTDS and do electromagnetic transfer simulations to study the effects on the energy industrial control system in terms of grid instabilities and different types of frequency and voltage fluctuations. And this is what we did 2021. So once COVID kind of we started after COVID was in 20. We went and took all the ISO's data in the US from the 7 independent system operators in the US, which have their data online. Essentially, we wanted to answer 2 questions. First question, which area in the US have seen largest load time during the COVID period? Why is that? I will explain in the second point. The answer to that was New York. So this is why you see New York ISO data, right? And specifically on April 11, we had the largest kind of load. Second question is want to implement in a simulation, like this load altering attack of this particular magnitude, right? Would it be easier in 2019 or 2020? Apparently, the answer is 2020 because you have low load kind of demand, but also low inertia because we have seen a lot of double generation increase in 2020. So what you see essentially in 2011, the spike that you see at around 200 seconds there, it is the same load altering attack between 2019 and 2020. But in 2020, if you implemented this whole load altering attack, you will essentially exceed over frequency kind of defined by operators or cause different shedding commands. Okay, so this was purely simulation, right? Not any theory by answering those two questions. The challenging thing is if you have a system, to answer where this attack needs to take place, right? And what would be the magnitude for this attack, right? Not simulation, because if you do simulation, it would be very difficult. So we wanted to find a way that we'll be able to answer this question for any type of system, right? So we modeled these dynamics of load altering attacks for a power grid model by a set of differential equations. So essentially, right? This is essentially the system model. And what you see here is that the system load into two components, right? And if I go to the next slide, this is what you'll see. We differentiated the system load into two components. One that we assume that is secure, right? System load that you cannot change. And one system load which is renewable, right? Over there, there is some controller that you can exploit and change the load. So under load altering attacks, the net load of the system is given by this equation, which epsilon to the power of L, it is the load altering attack component, which is less than equal to the essentially vulnerable part of those loads, right? So we wanted to characterize the system under those load altering attacks, right? So we wanted to find essentially closed form expressions to the system response to those load altering attacks. And based on the theory of second order dynamical systems, we were able to identify the response of the system to LLA of unit magnitude at the load pass I. What is this response of the system? Essentially, it is the generator phase angles and the generator and the elements of the fluctuations of the generator phase angles, right? Delta and omega. So essentially, we wanted to see the response on the frequency of the system based on having this type of attack of unity magnitude, right? And investigate essentially how the magnitude of those attacks will change as due to different load or inertia conditions. So omega max essentially shows here the maximum deviation from nominal, right? And then we wanted to answer what is the minimum load altering attack at this particular load pass that can cause these frequency exertions to be generated, right? So if you do that, this is essentially the equation that gives you this answer, right? But we want also to characterize this sensitivity to inertia conditions, right? So essentially, the sensitivity of this F, the response of the load altering attacks of unity magnitude to the changes of the inertia depends on agent value and agent sensitivities, and this is what you can calculate analytically. And Paolo before mentioned that you can essentially calculate something with fundamental frequency or get high order harmonics. What we wanted here essentially was a way to approximate, right, this response using some fundamental kind of components able to essentially estimate the location of those load attack and essentially the magnitude that you may compute that you may want to do as an attacker in order to lead those frequency exertions to the system, right? So what you see here is theoretically, right? Go and calculate this response of the system with the initial conditions and then this frequency sensitivity analysis using in regards to the inertia of the system. You can compute, right, that the least effort load alternate attack is given by this equation, the maximum given this estimated one, and also get the location of them, right? So if you do that theoretically, right, what you see here is you see a model system, right? And you see that the frequency fluctuations, right, for a load altering attack at pass 6, right, and the corresponding predictions do not vary far, right? So in theory and from the method that I just mentioned, what you see with green and blue, they don't vary far. So essentially, you can be able with this kind of approach to determine what will be the least effort load altering attack, but also the bus in the system that will cause this example. And the other thing I wanted to mention is the fact that low load conditions affect here, right? Renewable penetration is higher in 24 than 20, but also higher from midnight at 10 a.m. mainly offshore wind, right? And what you can see at the same kind of time period, load opening attacks is here can be, instantiated with less kind of amount of megawatt, right? So when you have low inertia in the system, it's much easier to cause attacks. And also when you have a higher mismatch, so the sigma here shows a mismatch between operation scheduling and load conditions, right? When you have a higher mismatch between those two, essentially with less magnitude of load altering attacks, it's possible to be implemented compared to having essentially a lower mismatch between residual load and generation scheduling. And then this is theoretical, but we went and validated that using SAT. Essentially, this is the case. Correct, right? The calculated by 6 essentially shows that this is the bus of the system that will cause the highest frequency fluctuations in the system due to load altering attacks compared to bus number 5. If you want to compare that, this is essentially what you see in bus 6 with blue and green. This is bus number 5, same kind of magnitude of load altering attacks, 18 megawatts, right? And different levels of wind fluctuation into the system, right? So theoretical analysis and simulations now can be validated, right? So essentially what we can do with this method, find the location and also know what will be the range of attack with that we want to alter our load. So in summary, right, what we have seen a lot of diverse generation and load profiles in the system, right, which gives a lot of opportunities if you do optimization and control stability, right, to study. Also, on the other hand, we have seen a myriad of extreme events, whether these events are weather conditions or cyber attacks. I like to call them as adverse kind of events, right? That poses also challenges for security and resilience of the system. So we need operational aware approaches. I think also that was mentioned by the previous speaker. We need to leverage system characteristics, testbeds to replicate and understand malicious actions, and we need solutions across the system stack, not just network, not just hardware, not just a system optimization. And the other thing I want to mention is I like to say nowadays that security is dead. Because we can do a little about how to respond to adversary actions. What we can do better is be able to define approaches that make the system better to respond to those reactions, right? We cannot control whether an attack will happen on the system or not, but we can control on how do we respond in such type of instances. So our mission in our lab, right, is to keep the lights on so we all can sleep peacefully. This is what I call perfection. And what we do, we work to secure the grid one faction at a time. And with that, I would like to thank you. I'll be happy to answer any questions. Thanks again.